Hello, historical geology students. I hope you had a great week. This is the second lecture for this week, February the 15th to February the 21st. We were talking about relative dating, and I gave you some examples of relative dating in the last video. Let's continue on that vein of thought. Take a look at this cross-section here in front of you. You should be able to do the relative dating, the historical geology for this type of cross-section. Don't get intimidated by this. Look at what you're take a good closer look at what you're seeing in front of you and use the principles of relative dating, principal superposition, original horizontality, lateral continuity, cross-cutting relationships and inclusions to try and determine the relative dating or the historical geology of this area. What do you see, first of all? Well, bed G is a sandstone because it has dots like this. That pattern means sandstone. This bed has angular pebbles in it. So this bed F is a breccia. Bed E is a shale because it's got dashes. Bed D is a limestone because it has this brick pattern with it. Bed C is a shale. Bed B is a limestone, and bed A is a shale. Notice also that bed G through C are folded. You got a wavy line, so this must be an unconformity. It was formed by uplift and erosion. Beds B and A are horizontal. So notice that the beds above the unconformity surface are horizontal, and the beds beneath the unconformity surface are dipping at a different angle. Okay, that's the first thing you should look at. And if you can't figure that out, turn off the video, try and figure out what you're looking at, and then turn the video and then fast forward the video and see if you can get that part yourself. Let's start off by talking about what happened first. What do you think happened first? Well, sandstone G was deposited because it's the oldest. It's on the bottom, according to the principle of superposition. Then what happened? Breccia B was deposited. Then what happened? What bed was deposited next? Well, shale E was deposited. What do you think happened next? Limestone bed D was deposited. Then what happened? Shale bed C was deposited. Tell me what happened next. Well, what must have happened next was beds G, F, E, D, and C were folded. We know that they must have been folded because after they were deposited because of the principle of original horizontality. These beds must have originally been horizontal, and then after they were deposited, they were folded. Tell me what happens next. Well, uplift and erosion. Whenever you have an unconformity, you want to list the uplift and erosion occurred next, and it formed what type of unconformity. You need to be able to recognize this on the test. Test number 2, and also on lab quiz number 2. You got sedimentary rocks above and below the unconformity surface, but they're dipping in different directions. So what kind of unconformity did you form? You should know this. It's an angular unconformity. Uplift and erosion formed an angular unconformity. Then what happened? Limestone Bed B was deposited. Then what happened? Last thing that happened is what? Shale bed A was deposited. That's the complete answer, ladies and gentlemen. Here's the surface of the earth, and this is what you see as you go deeper in the earth. You should be able to get the answer for this. Please take out a blank piece of paper and try and cover up these answers here and see if you work it until you can get these answers. If you do that, I guarantee you, you'll be much better prepared for the next test and the next lab quiz. Let's go to one that's a little bit harder, this one here, and see if you can do this one. Okay, take a good close look and see if you can see what's going on first of all. Rounded pebbles, this is a conglomerate. Dashes, this is a shale. All these symbols, by the way, are in your lab manual, or you can just watch the videos and I'll know that rounded pebbles is this conglomerate bed. Dashes is a shale bed. Brick pattern is a limestone bed. Shale bed. Conglomerate. Conglomerate. Shale. Conglomerate. Shale. And this whole thing is a shale. Where it says A, it's a shale. And then limestone was deposited on top of it. When you see this stippled pattern here, that means it's a plutonic rock. It's an igneous rock, and you can see how this dike has cut through all of these sedimentary beds. And deep underground, it would cut all the way down here, so it would have cut through all those sedimentary beds. And then this thing on top here is a lava flow. So this used to be the surface of the earth, and the lava flowed on top of this shale. Let's take, and you also got a wavy line here, so here's an unconformity. You got sedimentary beds dipping steeply to the west. This way is west, from left to right is west, from this way is east. So these beds are dipping or tilting. They're dipping to the west. Whereas these beds here are also dipping to the west, but at a gentler angle. Okay, now that we've examined our geologic situation for this cross-section, let's write what happened. Okay, see how they wrote C here? So they wrote C here to represent all of these beds underneath the unconformity surface. So you could simply write, a conglomerate was deposited, then shale was deposited, and limestone. But instead of that, for purposes of time in this diagram, I'll just say beds C were deposited. And that includes all of these beds. Then what happened? Uplift and erosion formed angular unconformity. Then what happened? Oh, actually, I'm sorry. I missed something. Beds C were deposited. Then beds C were tilted. Then what happened? Then you had uplift and erosion, forming an angular unconformity. Then what happened? Then this stack of beds was deposited. So then then conglomerate, shale, conglomerate, shale beds are deposited. Then this is a dike. You see this is a dike. So dike D and lava flow D cut through this bed C and all of this stuff. Then what happened? Then shale and limestone are deposited. So that's how you do a relative dating problem. First, you figure out what you're looking at, identify all the unconformities, look at all the sedimentary rocks, see which way they are tilting, and look for igneous rocks. That's how you do relative dating. Now, let's take a look at some pictures here. Here you got a photograph, and you might be standing 100 yards away looking at these three geologists. And what you want to first look at this picture, use your knowledge of geology to figure out what's going on. Here you can see that the beds are layered, so these are sedimentary beds. You automatically know that. Only sedimentary beds are layered. So these sedimentary beds, we can't really tell what they are because you're far away. You got to walk up closer to figure out what type of sedimentary beds they are. But we can clearly see they're tilted. They're not horizontal. So even before we walk up close to this outcropping of sedimentary rocks, we already know that these rocks here on the bottom are older and these on top are the youngest because of the principle of superposition. We also know that these sedimentary beds were laid down one at a time, and then later on they were tilted by an earthquake. Take a look at this picture, these two photographs here. This guy here is standing next to an interesting geologic feature, and he's looking. So you can't look deep in the earth here, but you're looking at the surface of the earth. So you got to first of all realize that you're looking at the surface, and that this rock continues down deeper into the ground. And this rock here is a granite. So it's an igneous rock. It's a plutonic rock that cooled underground. So, and then we have a darker or more mafic igneous rock cutting through the granite. So, using your knowledge of geology, try and figure out what's going on here. Well, you know granite is a plutonic rock. So this rock, first, it's got a phaneritic texture with big crystals in it. It's felsic because it's got a pink crystals in it of potassium feldspar. We also know that this must have cooled underground, so that the rocks that were above this granite have been eroded away, giving us a glimpse into the deep earth. We also know that this dike, it's made of gabbro, which is also phaneritic. It's got big crystals in it, so originally this was deep underground, but it clearly, the gabbro dike cuts through the more felsic granite. Which igneous rock is older here? You should know that the granite is older because it's cut by the gabbro dike. Now let's take a look at this picture here. This girl here is standing in front of an outcrop. So you're looking at here is the youngest rocks, and here's the oldest rocks, because they're all sedimentary beds. So we can use the principle of superposition and state that these sedimentary beds down here are older than these, which are younger, and they get younger as you go all the way to the youngest rocks on top. The other thing you notice is that the beds are tilted. They're not horizontal. They're not they're dipping, but they're not dipping very much. They're dipping a little bit, maybe 15 degrees to the west. So these beds are dipping. Also note, and this is very important, note the fault right here. Faults are always produced by earthquakes. Notice how these rocks here have moved down, and that's why you draw this half arrow here. What I mean by half arrow? Well, when you draw a fault, later on we're going to learn how to draw faults. Let me draw you a fault. Let's say you're looking at a picture and you see a bed of limestone and we draw limestone with this brick pattern. And we see that same bed of limestone on the other side of the fault. It's hard to draw neat with a Microsoft Word, but I'll give it my best shot. On the other side, remember you're looking at this, this is going deeper underground, so I'll just put a tree here. So you knew that's the surface of the earth. There's a tree. And there's a dog here, you can see. And there's a bird. And the dog is taking a piss on the tree. Let's draw that. I'm sorry. Anyway, this bed of limestone here has been displaced from this. This is the same limestone bed here and here. So what must have happened is when the earthquake occurred, this whole side moved up and this whole side moved down. Later on, we're going to learn how to draw these. These are called half arrows. We draw arrows like this to show which way moved up and down. We never do this. That means something else. We draw it like this. Anyway, here you can see these half arrows. This side moved down and this side moved up after the earthquake. So, tell me the historical geology of this area. Well, I could tell you, as a geologist, I've worked decades, longer than you've been alive probably, and I could tell these tan rocks are limestones, and these darker rocks are shales. So what happened was limestone was formed, then shale was deposited, then limestone was deposited, then shale was deposited, limestone was deposited, shale was deposited. Then what happened? Then the beds were tilted, and they were tilted so that they're dipping slightly to the west. Then the fault cut through all these beds. We know the fault came last because the fault cuts through all these beds, and that's the principle of what? Principle of cross-cutting relationships. Okay, so we're trying to use these, try and figure out relative dating in your lab manual. I'm going to send you a lab so you can practice doing this. We've already talked about there being two kinds of geologic dating: relative dating and numerical dating, which is also called absolute dating. Let's talk about absolute dating and the important scientific discovery of Marie Curie. Who is I'm sure you've heard of Madame Curie. And she's a really interesting historical figure. Who is Madame Curie? Well, as you could tell by the name, I don't know if any of you are taking French. Elle est française. She's French. But she's really Polish too, because her parents came from Poland and emigrated to France. And her husband is Pierre Curie. Madame Curie and was a remarkable scientist and a remarkable woman, because back in the late 1800s, it was unheard of for a woman to be um, a professor and a scientist of great renown. I really respect her because in a very male chauvinist society, she rose to the top. And I think she rose to the top for two reasons. One is she's extraordinarily intelligent. She had a firm grasp of chemistry. Two is her personality. She is a very likable person, and she was almost empathic. She could read people's what they were thinking, and I'm sure you know people like that. And um, just as the greatest American scientists usually are trained at places like MIT and Stanford and Caltech and Harvard and Yale and Princeton, and the greatest British scientists are trained at Cambridge or Oxford, and the greatest French scientists are trained at a series of universities called Les Grandes Écoles. And she was the first woman to get a PhD at Les Grandes Écoles. And she and her husband, there you can see her husband, Pierre, discovered radioactivity. We talked a little bit about radioactivity earlier on, where isotopes change into more stable daughters. Let's take a closer look at this. Let's see if I can go back here, and I'm going to erase all this crap. And we talked about isotopes before. For example, for uranium, there are different isotopes. All uranium has an atomic number of 92. And we always put the atomic number on the lower left-hand side of the elemental symbol and the atomic mass on the upper left-hand side. So in chemistry, we always put the atomic number on the lower left of the elemental symbol and the atomic mass on the upper left. And you already know by now that uranium-238 has 92 protons in it. And how many neutrons does it have? Well, what's 238 minus 92? 146 neutrons, right? However, there is another type of uranium and that other type of uranium. Let me get this draw here. Put this back. So that's one type of uranium. There's another type of uranium, but instead of saying type, we're going to use the word we use in chemistry. There's another isotope of carbon called uranium-235. It's different than uranium-238 because it has a lower atomic mass. It's still got 92 protons in it, because if it doesn't have 92 protons in it, it's not uranium. An element always has the same atomic number, but isotopes are variants of the same element with a different atomic mass. And the difference is uranium-235 has less neutrons in it. It has how many? It has 133 neutrons in it. Right? Okay. There is a third isotope of uranium, and it's called uranium-234. Uranium-234 has one less neutron in it when compared to uranium-235. It has a total of how many neutrons? 132. And in chemistry, we say that uranium-238 is the heaviest uranium isotope because it has the highest atomic mass. And uranium-234 is the lightest uranium isotope. Well, radioactive isotopes change into lighter isotopes, which we call daughters. Let me show you how that happens. For example, uranium-238 is radioactive. It's unstable. Unstable radioactive means the same thing. And it changes into its daughter. Who's its daughter? Well, its daughter is, and you can go look at your periodic table, what element, look at your periodic table, please, and what element has an atomic number of 90? Thorium, Th. And this is the atomic mass and the atomic number of thorium-234. So uranium-238 is unstable, which we say radioactive. It's radioactive, and it changes into its daughter, thorium-234. And it releases a particle called an alpha particle. Alpha is the first letter in the Greek alphabet. We use Greek letters in math. An alpha particle has an atomic mass of 4 and an atomic number of 2. If you look at your periodic table, here you can see the periodic table. Uranium has an atomic number of 92. Thorium has an atomic number of 90. What element has an atomic number of 2? Do you know? Well, let's see. Let's take a look here. The element that has an atomic number of 2 is this one here, helium, He. He, helium, has an atomic number 2. So in effect, an alpha particle is a helium atom with an atomic mass of 4 and an atomic number of 2. This type of radioactive decay is called alpha decay. Let's write that down because it's important. Alpha crap. I'm going to just type it. Okay, the wheel's spinning, so let's see here. We call this type of radioactive decay alpha decay. This is the first type of radioactive decay that we need to learn about. It's called alpha decay. Now, alpha decay is a type of radioactive decay where the parent produces a daughter, and the daughter always has an atomic number of -4 from the parent and -2 from the daughter, and it releases this particle called an alpha particle. It's not complicated, ladies and gentlemen. People get intimidated by chemistry. Notice that the atomic mass of the daughter plus the atomic mass of the alpha particle is 234 plus 4 is 238. The atomic number of the daughter plus the atomic number of the alpha particle, 90 plus 2 is 92. It has to be that way because there's a law in physics called the conservation of mass. You don't lose protons or neutrons. And so you didn't lose any. You're simply, the parent has released 2 protons, and therefore the atomic number of the daughter is -2. And it's released 2 neutrons. And so if 2 protons plus 2 neutrons are lost, the atomic mass must go down by 4. Let's see if you got this here. Let's go back to our periodic table. Excuse me. And we're going to look at another element called radium. Radium has an atomic mass of radium, Ra, has an atomic mass of 226. So let's write that in. And what's the atomic number of radium? It is 88. So the atomic number of radium is 88. Okay, before we figure out this alpha decay, tell me how many protons are in a radium atom. 88. Number of protons is equal to the atomic number. How many neutrons are in a radium atom? 138, right? Okay, should be able to do that by now. Now here's the question I got for y'all, and I know you can do this. If radium-226 undergoes alpha decay, so that it makes a alpha particle. My question for y'all is, who is the daughter? What do you put in this box? Who's the daughter of radium-226? Well, it must be -4 with every alpha decay. So the atomic mass of radium must be what? 222 -4, right? 226 -4 is 222. And what's the atomic number of radium going to be? 88 -2 is 86. So to figure out who the daughter of radium-226 is, you need to find an element with an atomic number of 86. And if you look at the periodic table, you'll find who the daughter is. So there's the periodic table. And what you'll find is that there's a daughter with a atomic mass of 86, and it's Rn, radon. Okay, so radium-226 undergoes a type of radioactive decay called alpha decay. It produces an alpha particle and a daughter, radon-222. That's the first type of radioactive decay that you need to do. When a radioactive parent releases 2 protons and 2 neutrons, it makes an alpha particle and a daughter with an atomic mass of -4 and an atomic number of -2. Now we're going to talk about another type of radioactive decay that you need to know about, and it's called beta decay. Alright, this alpha particle is the release of 2 protons and 2 neutrons from the nucleus of a radioactive parent. A beta decay involves the release of an electron called a beta particle from the nucleus of a radioactive parent. And the type example I'm going to give for you to understand what beta decay is, let's take a look at a common radioactive isotope called carbon-14. What's the atomic number of carbon-14? 6. What's the atomic mass of carbon-14? 14. How many protons are in a carbon atom? A carbon-14 atom? 6. How many neutrons are there in a carbon-14 atom? 8. 14 minus 6 is 8. Now, carbon-14 releases something called a beta particle. And beta is the second letter in the Greek alphabet, and it looks like this. As I mentioned before, a beta particle is an electron released from the nucleus of a radioactive parent isotope. You might ask yourself, and you should ask yourself, you told me that there are no electrons in the nucleus of an atom, and you'd be right about that. There's only protons and neutrons in the nucleus of an atom. So how can the nucleus of an atom release an electron? Well, think about it. A neutron is what? A neutron is a proton plus an electron. So if you split a neutron, you can release an electron. And that's what beta decay involves, the splitting of a neutron in the nucleus of a radioactive parent, releasing an electron, so that the net result of beta decay is you lose a neutron, but you gain a proton. I'll repeat that. Beta decay involves the losing of a neutron and the gaining of a proton. A proton and the neutron weigh the same, right? So beta decay will not change the atomic mass. But you've gained a proton. So the daughter that's produced from beta decay will have the same atomic mass, but the atomic number is going to go up by 1 because you gain a proton. So the atomic number of your daughter is going to be 7 for carbon-14. And looking at this chart, 7 is nitrogen, N. Bottom line is beta decay is a type of radioactive isotope decay where the atomic number goes up by 1 and the atomic mass stays the same. Carbon-14 changes into nitrogen-14, its daughter, through beta decay. Uranium-238 changes into its daughter, thorium-234, through alpha decay. And the rate at which parent isotope changes into daughter can be measured mathematically using a measure called half-life. Every radioactive isotope has its own half-life. For example, the half-life of carbon-14 is 5,730 years. What does that mean? Well, what that half-life is the amount of time, and I could people have a hard time sometimes understanding this in their mind. Other people get it like that, but I'm going to repeat it a couple times, and then I want you to think about what half-life is. Half-life is the amount of time it takes for half of the radioactive isotope atoms in the sample to change into daughter atoms. I'll repeat that. Half-life is the amount of time it takes for half of the radioactive isotope atoms in a sample, such as a rock, into daughters measured in years. So if the half-life of carbon-14 is 5,730 years, that means the amount of time it takes for half of the radioactive carbon-14 atoms in your sample to change into nitrogen-14 is 5,730 years. And here's a way you can visualize it. Imagine a rock has carbon-14 in it. When that rock first forms, there are no daughters in the rock because there hasn't been any time to make any daughters. So if you have 1 million carbon-14 atoms represented by blue marbles in a rock, you've got 1 million blue marbles and no red marbles. The red marbles are nitrogen-14. But after 5,730 years have gone by, you'd have 500,000 blue marbles and 500,000 red marbles. In other words, you'd have 500,000 carbon-14 atoms and 500,000 nitrogen-14 atoms in your sample. If another 5,730 years has gone by, in other words, if another half-life has gone by, then how much of the original carbon-14 do you have left? What's a half of a half? A quarter. So after one half-life goes by, you have 1/2 of your original parent and 1/2 daughter. And for this specific case, it would be 1/2 carbon-14 and 1/2 nitrogen-14. Right? After 2 half-lives have gone by, and by the way, 1 half-life for carbon-14, this is after 5,730 years. After 2 half-lives have gone by, you'd have 1/4 parent and 3/4 daughter. And that means how much time has gone by? What's 5,730 times 2? 11,460 years have gone by. After 3 half-lives have gone by, how much of the original parent do you have left? What's a half of a half of a half? 1/8, right? So you'd have 1/8 parent left and 7/8 daughter. Or if you like to use percentages, you'd have 12.5% parent and 87.5% daughter. Or if you like to use ratios, you'd have 1 parent to every 8 daughters, 1 parent for every 7 daughters. And how much time would have gone by? Whatever 3,000, 5,000, 5,070, 5,730 is. That's how much time would 7,900. Anyway, I'm not going to do that. So whatever that number is, put it in your calculator. Do you see how that works? Okay. Let me give you a test question to see if you can figure out if you understand what a half-life is. Here's your question. If a rock contains 87.5% of a 87.5 of a parent isotope and 12.5% of a daughter isotope, and the half-life of the parent isotope is 2 million years. How old is the rock? Also, how many half-lives have gone by? Okay, can you answer this question? Try and answer this question. Well, first of all, let's look at what's given to us here. The half-life of an isotope is 2 million years, right? So we know that. Half-life is 2 million years for this isotope. If you have if you have, I made a mistake. Okay, you have 12.5% parent left and 87.5% daughter left. How many isotopes, how many half-lives have gone by? Think about it. How many half-lives have gone by? Well, after one half-life, how much parent isotope do you have left? 50%. After two half-lives have gone by, how many half-lives have gone by? 2 half-lives. After 3 half-lives have gone by, you'd have 12.5% parent. So how many half-lives have gone by? 3 half-lives have gone by, right? 1 half-life is 2 million years. But 3 half-lives have gone by. So how old is the rock? Think about it. 3 half-lives have gone by, and 1 half-life is 2 million years. So your rock is how old? 6 million years old. You should be able to do something like that. Let's give you another problem and see if you can figure it out. If a rock contains 500,000 radioactive parent atoms and 500,000 daughter atoms, and the half-life of the radioactive parent is 500,000 years, how old is the rock? Also, how many half-lives have gone by? Try and figure that out in your head. If a rock contains 500,000 radioactive parents and 500,000 daughters, then you have 50% parent and 50% daughter in your rock, right? How long is one half-life? 500,000 years. So, how many half-lives have gone by if you have one half parent and one half daughter in the rock? One. One half-life has gone by. How old is your rock then? One half-life is how much? One half-life is 500,000 years, so that your rock must be 500,000 years old. Try and do these. I'm going to send you some video links so you can understand this concept of half-life. And then also I'm going to send you one on relative dating. And I'm going to send you another one on alpha and beta decay. I'm going to make another video for you later.